Another day, another story. Can you explain this like I'm a first-year collage chemistry student? Yes, of course. The synthesis of amides from carboxylic acids and amines involves a condensation reaction, where water is eliminated to form the amide bond. The reaction is typically catalyzed by a coupling reagent such as dicyclohexylcarbodiamide, DCC, which helps to activate the carboxylic acid and facilitate the reaction. Here's the balanced chemical equation for the reaction. Cu plus RNH2 plus DCCuCon plus dicyclohexylurea. In this equation, R represents an alkyl or aryl group, and dicyclohexylurea is a byproduct of the reaction. The mechanism of the reaction involves the following steps. The DCC catalyst reacts with the carboxylic acid to form an activated intermediate called an O-acylosurea. The amine acts as a nucleophile and attacks the activated intermediate, resulting in the formation of an amide intermediate. The intermediate undergoes intramolecular dehydration to eliminate a molecule of water and form the final amide product. Overall, the reaction of carboxylic acids with amines to form amides is an important transformation in organic chemistry that can be used to synthesize a wide variety of amide compounds for use in pharmaceuticals, agrochemicals, and materials science. Sure. So, let's start with the basics. Organic chemistry is the study of compounds that contain carbon atoms. One important class of organic compounds is called amides. These are molecules that contain a nitrogen atom bonded to a carbonyl group, a carbon atom double bonded to an oxygen atom, and to another carbon atom. Now, let's talk about how amides are made. The process involves two types of molecules, carboxylic acids and amines. Carboxylic acids are organic compounds that have a carboxyl group, Cu, at the end of their carbon chain. Amines are organic compounds that contain a nitrogen atom bonded to one or more alkyl or aryl groups. When carboxylic acids and amines react together, a molecule of water is eliminated, i.e., removed, and an amide bond is formed between the carboxylic acid and the amine. This reaction is called a condensation reaction. To help facilitate this reaction, a coupling reagent like dicyclohexylcarbodiamide, DCC, is often used. DCC helps activate the carboxylic acid by forming an intermediate called an O-acylosurea. Then, the amine acts as a nucleophile, attacking the activated intermediate and forming an amide intermediate. Finally, the intermediate undergoes intramolecular dehydration, i.e., loses a molecule of water, to form the final amide product. So, in summary, the synthesis of amides from carboxylic acids and amines involves a condensation reaction that forms an amide bond and eliminates a molecule of water. The reaction is catalyzed by a coupling reagent like DCC, and the mechanism involves several steps including the activation of the carboxylic acid, nucleophilic attack by the amine, and intramolecular dehydration. Explain more about carboxylic acids are organic compounds that have a carboxyl group, Cu, at the end of their carbon chain. Amines are organic compounds that contain a nitrogen atom bonded to one or more alkyl or aryl groups. Sure, let me explain a bit more about carboxylic acids and amines. Carboxylic acids are a class of organic compounds that contain a carboxyl group, Cu, at the end of their carbon chain. This carboxyl group is composed of a carbonyl group, a carbon double bonded to an oxygen atom, and a hydroxyl group, O. The general formula for a carboxylic acid is Ru, where R represents an alkyl or aryl group. Carboxylic acids are important because they are involved in many biological processes. For example, acetic acid is a carboxylic acid that is involved in the production of energy in cells. Other carboxylic acids are important components of fats and oils. Amines are another class of organic compounds that contain a nitrogen atom bonded to one or more alkyl or aryl groups. Amines can be classified as primary, secondary, or tertiary, depending on the number of alkyl or aryl groups attached to the nitrogen atom. The general formula for a primary amine is RNH2, where R represents an alkyl or aryl group. Amines are also important because they are involved in many biological processes. For example, neurotransmitters like dopamine and serotonin are amines that are involved in the transmission of signals between nerve cells in the brain. Other amines are used as drugs, such as the antihistamine diphenhydramine. In summary, carboxylic acids and amines are both important classes of organic compounds that are involved in many biological processes. Carboxylic acids contain a carboxyl group, Q, at the end of their carbon chain, while amines contain a nitrogen atom bonded to one or more alkyl or aryl groups. Explain more about when carboxylic acids and amines react together. A molecule of water is eliminated, i.e., removed, and an amide bond is formed between the carboxylic acid and the amine. This reaction is called a condensation reaction. Sure, let me explain in more detail how the reaction between carboxylic acids and amines works. When a carboxylic acid and an amine react, the carbonyl group of the carboxylic acid, Q, reacts with the nitrogen atom of the amine, NH2, to form an amide bond, CON. During this reaction, a molecule of water, H2O, is eliminated, which is why this reaction is called a condensation reaction. The reaction can be catalyzed by a coupling reagent such as dicyclohexylcarbodiamide, DCC. DCC activates the carboxylic acid by converting it to an intermediate called an O-acylsuria. This intermediate is then attacked by the nucleophilic nitrogen of the amine, forming the amide intermediate. The elimination of water to form the final amide product is typically facilitated by an acid catalyst, such as hydrochloric acid. Overall, the reaction between carboxylic acids and amines to form amides is a useful and widely used transformation in organic chemistry. It is used in the synthesis of many important compounds, such as pharmaceuticals, agrochemicals, and materials science. The ability to selectively control the formation of amide bonds is a key step in the development of these compounds. Explain, to help facilitate this reaction, a coupling reagent like dicyclohexylcarbodiamide, DCC, is often used. DCC helps activate the carboxylic acid by forming an intermediate called an O-acylsuria. Then, the amine acts as a nucleophile, attacking the activated intermediate and forming an amide intermediate. Finally, the intermediate undergoes intramolecular dehydration, i.e., loses a molecule of water, to form the final amide product. I want more detail on dicyclohexylcarbodiamide, DCC, and O-acylsuria. Sure, I can explain in more detail about dicyclohexylcarbodiamide, DCC, and O-acylsuria. Dicyclohexylcarbodiamide, DCC, is a coupling reagent commonly used in amide bond formation reactions. It is a molecule composed of two cyclohexyl rings connected by a central carbon atom that is doubly bonded to two nitrogen atoms. DCC acts as a catalyst in the reaction by activating the carboxylic acid and facilitating the formation of the amide bond. In the presence of DCC, the carboxylic acid reacts with the DCC to form an activated intermediate called an O-acylsuria. This intermediate is formed when the DCC attacks the carboxylic acid to form an unstable intermediate, which then rearranges to form the O-acylsuria. The O-acylsuria intermediate is highly reactive and can undergo further reactions, such as reaction with the amine to form the amide intermediate. The amine then acts as a nucleophile and attacks the carbonyl carbon of the O-acylsuria intermediate. This results in the formation of an amide intermediate, which is stabilized by resonance delocalization of the nitrogen lone pair of electrons into the carbonyl group. Finally, the amide intermediate undergoes intramolecular dehydration, which means that it loses a molecule of water, H2O, from the reaction. This is the final step of the reaction, and it results in the formation of the amide product. Overall, the use of DCC as a coupling reagent helps to activate the carboxylic acid and facilitate the reaction between the carboxylic acid and the amine. The O-acylosauria intermediate formed by DCC serves as a highly reactive intermediate that allows for efficient amide bond formation. What is it? Is a molecule composed of two cyclohexyl rings connected by a central carbon atom that is doubly bonded to two nitrogen atoms. Show me the chemical buildup. Sure, here's the chemical structure or formula of dicyclohexyl carbodiamide, DCC. Makefile copy code. H2N equals C equals NH, C6H11, C6H11. As you can see, it is composed of two cyclohexyl rings connected by a central carbon atom that is doubly bonded to two nitrogen atoms. The nitrogen atoms are also each singly bonded to a hydrogen atom. Can you show me another example of how a chemical reaction would look? Sure. Here's an example reaction showing the formation of an amide bond between acetic acid and butylamine, catalyzed by DCC. Net copy code. Chiku plus C4H9NH2 plus DCCCH3 cocaine C4H9 plus N, undicyclohexylurea. In this reaction, acetic acid, Chiku, and butylamine, C4H9NH2, react with DCC to form an activated intermediate, an O-acylosauria. The butylamine then attacks the O-acylosauria intermediate, forming an amide intermediate, which then undergoes intramolecular dehydration to form the final amide product, N-butylacetamide, CH3-cocaine C4H9. The reaction also produces a byproduct, N-undicyclohexylurea. Overall, the reaction can be summarized as acetic acid plus butylamine plus DCC and butylacetamide plus N-undicyclohexylurea. Can you explain the butylamine then attacks the O-acylosauria intermediate, forming an amide intermediate, which then undergoes intramolecular dehydration to form the final amide product, N-butylacetamide, CH3-cocaine C4H9. The reaction also produces a byproduct, N-undicyclohexylurea. Certainly. After the DCC reacts with the carboxylic acid to form an O-acylosauria intermediate, the amine, in this case, butylamine, acts as a nucleophile and attacks the activated intermediate. This results in the formation of an amide intermediate, where the carboxylic acid is now bonded to the amine through an amide bond. Next, the amide intermediate undergoes intramolecular dehydration, which means that a molecule of water is eliminated from the molecule. This dehydration reaction is facilitated by the nitrogen atom in the amide group, which helps to stabilize the transition state of the reaction. The elimination of water leads to the formation of the final amide product, N-butylacetamide. This molecule contains an amide bond between the carboxylic acid group, now in the form of an acetate group, and the butylamine group. The reaction also produces a byproduct, N-undicyclohexylurea, which is formed from the reaction between DCC and any excess carboxylic acid or amine that may be present in the reaction mixture. More. In addition, the formation of the amide bond is an example of a condensation reaction, which involves the elimination of a small molecule, in this case, water, to form a larger molecule. The formation of the amide bond is energetically favorable because it involves the formation of a more stable molecule with a lower energy state than the starting materials. The use of DCC as a coupling agent in this reaction is important because it helps to activate the carboxylic acid and promote the reaction with the amine. DCC reacts with the carboxylic acid to form an O-acylosauria intermediate, which is more reactive towards the nucleophilic attack of the amine. Without the use of a coupling agent, the reaction between the carboxylic acid and the amine would be slower and less efficient. Overall, the synthesis of amides from carboxylic acids and amines is an important transformation in organic chemistry that is widely used in the pharmaceutical, agrochemical, and materials science industries. The ability to selectively form amide bonds between different functional groups is a critical step in the development of many new drugs, pesticides, and materials. What is agrochemical? Agrochemicals are chemical substances used in agriculture to enhance crop production and protect crops from pests, diseases, and other environmental stressors. Examples of agrochemicals include fertilizers, pesticides, herbicides, insecticides, and fungicides. These chemicals can improve soil quality, promote plant growth, and increase crop yields, ultimately contributing to food security and the sustainability of agriculture. However, the use of agrochemicals can also have negative environmental impacts, such as pollution of waterways and damage to non-target organisms, and their use is subject to regulation and oversight by government agencies in many countries. Thanks for watching. Please like and subscribe.